timing. Oh, excuse me. So, I oftentimes get people, particularly after watching that nomenclature video, point out there's no way that they would possibly ever have the time to show all of their work in a full process of going through and doing these things. Number one, you shouldn't have to show your work. If you've done enough practice, you can get to the name very fast. You can get to the formula very fast. Okay, so that's the first argument. Do the work by putting in all that effort, showing all that content behind it. You'll get through your names so much faster, okay, once you've done that practice. So then the next part that I would usually challenge is the only reason it's taking a long time is because you're hemming and hawing over whether or not you should show work. You need to write down your work all the time, every time. Right? There's no maybe I shouldn't do it. Okay. And to that end, we're now at 1 minute into the video, and I'm going to show all the work for everything that we're looking at here. So, and I'll even talk through it. We've got chromium with oxygen. Because we're in a compound, that ending needs to change to an ide, so it becomes oxide. For those of you looking, I'm now actually going to move to the next one. Why? Because I know I have multiple questions, and if I purge this useful information down, dang, I did it again. Oxygen needs to become oxide. I can think slower later on. Next one, we got carbon, oxide. Hey, this is easy. Di means 2, tri means 3. I guess I really should color code those. So there's the di, there's the tri. So cool, look at that one. That one's actually done. Lead 4, that 4 is the charge, so I'll put that down there. Acetate, dang, that's a complicated one. That would be C2H3O2. I already specified the charge for lead, so I'm probably going to have to need it for acetate, so I'm going to go ahead and drop it in there. Now, let's take a moment, pause. Where do I want to go? Let's go up to the top. Lie, not to the top, because that one's hard. 2 and 5. This is coming from nitrogen and oxygen, both being nonmetals. Because they are nonmetals, that is a covalent compound, and just like the tricarbon dioxide, I can use Greek prefixes. This is one I almost always get wrong. Is it pentoxide or pentaoxide? I never really remember. You don't get graded for spelling, so don't stress about it. So now I've got these two done, and I'm left with the two hardest that have a metal, which means we're looking at ionic compounds or ionic bonds, and that makes it a lot more challenging. I think there's more information in the bottom one, so I'm going to go through and figure that out. What I need to know is how much of each of those species go in there. Well, I know the charges have to cancel. I know that this must be true. Okay? And those have to equal 0 because that's what our compounds have to do. Well, x and y, that's two variables, one equation, infinite amount of solutions. I'm just going to start guessing. I'm going to say x equals 1. When I go through and say guess x equals 1, I get 4 minus y equals 0. Admittedly, I did take a little bit of time there to shortcut that. Okay? So maybe that's not fair. 1 times 4 plus y times minus 1 equals 0. That 0 is falling off the page there. If I try to set this up, holy junks. I intended to guess the wrong one. If we flip that around, I get y equals 4. What does that mean? I have whole numbers. I can actually do the substitution into that. And my formula for the lead acetate, lead X we said was 1. The acetate C2H3O2, we said that that was a 4. Whoa, what is C2H3O24? That doesn't make sense. Let's include some parentheses there. Sweet, now I've got that separated. Third one now done off the list, and we're just barely at 4 minutes in. The next one becomes a lot harder. If we go through and set this up, I have 2 chromiums times an unknown charge plus 3 oxygens. Oxygen has a -2 charge. This has to equal an overall 0. Where does that take me? I would say 2x minus 6 equals 0. 2x equals a positive 6. X equals a 3. What did I say X was? X was the charge on the chromium. That charge gets specified 1, 2, 3. We're at now 5:30. We're 4.5 minutes in, and I solved 4 questions with work. Okay? I do this, I've now done this multiple times, but the point behind this is you can show work. You can put work in. Okay? And yes, it takes time, but it gets you the answer right. Helps if we actually write down what we did. All right, that was chromium 3 oxide. So spend the time to do the work. Write that all out. The time to be doing that is during the homework, so that when you get to the exam, you don't have to show all the work. One of the things that is very misleading with a lot of content within the sciences is that the people teaching it are teaching it because they know the answer, and it makes it so much easier to get there. You don't know the answer, which means you need to have a process of showing the work to get you there. So please, 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 your work should be there. You should have messy stuff like this shown on this slide. Okay, you really should. Okay. With that, that's the end of me doing practice on that. It might be useful to do some more practice. To that end, the lab has a bunch of practice. Internet has tons of practice. Right? So pull up random things and just start trying to name some compounds. There are plenty of names out there that you won't be able to name. Don't worry about those. Right? And those can be hard to find. So if you're just going to look for practice, general chemistry, nomenclature, you should be good. Okay? So you need help with this? Our tutoring center is awesome. Take a look at our Canvas page. There's a tutor/learning center link. Click that, go out to get that help. Get that help from our embedded tutor. Sign up to have office hours with him. He's fantastic. While doing that, ask for the pink sheet, which it's not pink because we're all digital right now, but it has a naming flowchart on it. So if you say maybe pink sheet naming flowchart, hopefully our tutors in the tutoring center will know what you're talking about and be like, oh yeah, here, let me get you that handout, and they'll get you a digital copy of it. Okay. The next thing that you could do is take a look at our lab Canvas module, week 6, naming and writing compounds. And in fact, some of you may not be in the lab. Let me know, and I'll try and get that incorporated into our Canvas site. So we've got that page that has those. Those of you are like, but I'm not in Mike's lab. Doesn't matter. I wrote all the labs. So if the labs suck, that's my fault, not the people teaching it. Okay. So that content was all put together by me, and it has kind of that flow chart behind it. I will add as kind of a note, particularly when we look backwards at that acetate, that's technically a ternary ionic compound or a polyatomic ion, and those are more things to go through and memorize. Right? There are some that I think are critical to memorize. Okay, they're identified in that nomenclature video that you watched, that hour-long struggle to get through. There's stars next to them from a figure that came from your textbook. Okay, if you're doing just general practice, use your textbook. Take advantage of that resource and have that in front of you when you go through and do your nomenclature practice. Okay. Next little bit of content are compounds and formulas. We take a look at this structure. Okay, this structure might very well be why you're awake right now. It's caffeine. Okay, and if we look at caffeine, having to draw out that Lewis structure to talk about it could be really tedious if we had to do a whole bunch. Okay, so what we tend to do is come up with approximations or simplifications, and that simplification would be looking at a chemical formula. So we could go through and note, well, this compound has carbon, it has hydrogen, it has nitrogen, and it has oxygen. Okay. Well, is it just one carbon, one hydrogen, one nitrogen, one oxygen? No. Okay. Well, let's add more information into our formula. 1, 2, 3, 4, 5, 6, 7, 8. Hopefully I counted that right. We get 8 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I should have closed the door if you're picking that audio. And then the last one, or not last one, nitrogen. 1, 2, 3. And now our last one, our oxygen, 1, 2. And we would now have a chemical formula for caffeine. And we could use that in our calculations or in writing out our text. Okay, that can make life a little bit easier. Okay, so that's the point of a chemical formula. It tells us each of the elements that are present, and then it also tells us the number, okay, of atoms of that element, okay, in the whole thing. Okay, so that's the point of that chemical formula. That's useful information, and as we'll see in the next unit, Unit 3, okay, that information you're going to be expected to call up to actually do conversions. Okay, so let's take a look at some potential formulas. H2O, what are we talking about? H2O, we have 2 hydrogens combined with 1 oxygen, and that makes the compound H2O. That compound we would also refer to as water. Okay, water would be now the common name for that. Okay, we could also refer to it as dihydrogen monoxide. And if you're bored or you're just curious, look up the hazards for dihydrogen monoxide. Just Google dihydrogen monoxide. Man, it'll blow your mind at how ridiculously dangerous dihydrogen monoxide is and make you wonder why we allow people to drink that every day. That's water. That's water. C6H12O6. Okay, it looks kind of dangerous. That's sugar. Okay, that's the stuff that we're probably ingesting way too much of. Okay, if we kind of move through, you start to notice perhaps some patterns. Hydrogen came before oxygen. Hydrogen came before oxygen. Hydrogen came before oxygen. Wait, what the? Why are we pulling that hydrogen out? Okay, well, if we threw a little AQ behind this, and you were really on top of that nomenclature video, you might note that this is acetic acid. By placing the hydrogen in a different location, we're calling attention to its chemistry. So our chemical formulas can hold some secondary information. It's not always just smash the elements all together. We could change the order and parsing on where those things are located to help us kind of understand and interpret maybe some chemical reactivity. We move to the next one. Note that we throw the H out at the end. Okay, well, why are we throwing it out at the end? In front made sense because we had an acid. Well, this one's not an acid, but what I'm trying to show is the hydrogen is connected to the oxygen. Okay, so the placement of those individual atoms, I want you to realize can change in varying circumstances, and that's going to depend on that particular circumstance. So don't stress a whole lot about that placement. Okay, as far as you're concerned with nomenclature and our formulas, metal, non-metal, everything else is kind of explicitly told to you in the sequence in which we name those individual things. Okay, so we'll throw in 2 more things. We take a look at the lower left. CH3CO2H. Again, we're trying to show, as we did over here, a little bit of that connectivity. For those of you being really, really cognizant of what's going on here, that's C2H3, we color code this out, O2H. Those 2 formulas are representing the exact same compound. Not obvious when you look at the formula. Okay, so again, consider that your formulas can be a very dangerous thing to overanalyze. They're giving you some information. Depending on who's putting together the formula, they may be giving you more information than is inherently obvious. That's going to come with practice. So don't freak out at them. Just realize sometimes they've got more information than you think. This gets layered on even more, which we'll do in this unit, when we look at a chemical reaction. So now where we place those things in a sequence and how much spacing we're putting in between is now going to change our interpretation of it. Okay? Another quick example that I've sometimes have used in the past, you even go up to this H2O. Am I now referencing water? Well, probably not. There's enough of a gap here that you're like, well, that's probably not water. That's probably H2 separated from oxygen. Right? Well, what if I put the oxygen here? Is that still two separate things? What if I put it here? What if I put it here? What if I put it here? Okay. The spacing in between those symbols can make a really big difference. Okay, so be aware of that when you try and write things out and when you interpret things. If you're seeing kind of an odd spacing, it's probably because someone is trying to show that they are different pieces. Usually best to throw a mathematical operator in there, like a plus sign or an arrow, to help show that there's different pieces within it. Okay, but that doesn't always happen. Okay, with that, this video was way longer than I wanted it to be, so I'm going to go ahead and call it here. Thank you for listening.